Two terms. Basically, there's two different types of scenarios that you're either going to have a greatest common factor or you're going to have a difference of perfect squares. And we'll kind of go through both of those. It may start off with two terms that you may have something like this, where that you have 2x to the third, and we'll actually go back and do some more stuff with greatest common factors in a little bit. But we may have, for just two terms, it's either one of two options. It's either greatest common factor or different perfect squares. All right, and again, if we're talking about difference, greatest common factors, if you take 2 and 6, of course, you can divide them both by 2. So that basically what we're going to do is you're going to figure out what that greatest common factor is first. So 2 and 6, you can divide them both by 2. They both have an x in common. And again, if you're talking about greatest common factor, you take the smallest amount of x. So if you've got x to the third and x to the second, then we're going to take out x to the second. All right, so if we're talking about those two terms, your greatest common factor would just be 2x squared. Now, they're going to ask you in some cases to either find the greatest common factor and then factor completely. And if they ask you then to go ahead and factor completely, which is pretty much what we're going to do, you're going to take whatever this greatest common factor is, and you're going to divide by that greatest common factor. And then whatever's left over, that's what we're going to put in the parentheses. So if we do 2 divided by 2, that's basically 1. If you've got x to the third divided by x squared, that's going to leave you with an x that's here. Then you've got negative 6 divided by 2, which is negative 3. In that case, all the x squareds would cancel out. So then that would be your answer in factored form. All right, now most of the two terms you have, now you have kind of a mix of that one, but most of the ones that we do with two terms, they're really going to be different to perfect squares. That basically this is like a special kind of factoring that you'll kind of do just based on what you have there. And again, we'll come back and do some more greatest common factor stuff in a little bit. That we'll actually do greatest common factor and then like do all the options we could do. But let's say we've got x squared minus 49. All right, so real quick on this one, you can tell, all right, there is no greatest common factor because this is 1 in 49. There's nothing we can do with it. When you're looking for a difference of perfect squares, now this only can be a difference. It can't, plus doesn't work. So it always has to be that's just a subtraction with two perfect square numbers. And if you think about what perfect square numbers are, x squared is x times x. 49 is 7 times 7, right? So as long as the numbers you can get to is the same thing multiplied by itself twice, which again is the perfect square part of it, then your shortcut answer is the x that's here is going to go first in the parentheses. And then the 7 will go second. But if it's a negative 49, what combination of numbers sign-wise does it have to be if it's going to be a negative number? Yeah, you're going to have one that's got to be negative. The other one have to then be a positive. So over here, you have a negative, and then you're going to have a positive. And that's it. And most people go, what do you mean that's it? That's it. That's all you do. Because it has to be, it's a number times itself. Second one's a number times itself. And then it's always, this thing will be, the first number will be first. The second number will be second in parentheses. And again, one's a plus, one's minus. Which one you put first, it doesn't matter. It's just, that's all it's going to be. Most people go, it's that easy? Yeah, for the most part it is, yeah. Now they always throw a little twist, a little curve to you here and there. So if you had y squared minus 100. Y squared is y times y. 100 is 10 times 10. So it's going to be y plus 10 and y minus 10. Now, somebody that's pretty, yeah, most part it's going to be pretty easy. 4t squared minus 81. All right, so if you've got 4t squared, now we know t squared would just be t times t. But if you've got 4t squared, Okay, that's 2t times 2t. And 81 is 9 times 9. So that would be 2t plus 9 and 2t minus 9. All right. Now, here's where you have to start kind of tweaking things a little bit. Hopefully, we can get 2 in here. I think we can. Everybody good so far?
Yeah.
It's pretty straightforward, right? I mean, you just something times itself, something else times itself, and it's got to be a minus in the middle, and then basically break it down. A couple of things they'll do different to kind of mix it in. Maybe it's 2x squared minus 50. And you go, and then the first thought is, well, okay, 50, there's nothing you can do times itself to get 50, right? So here's what you do for 2 terms. Before you do the perfect squares, you always look for a greatest common factor first, every single time. Because you've got 2x squared and 50, right? So you could factor out of 2. So divide both numbers by 2, that'll leave you with x squared and 25. And forget about the 2 for a minute. That's perfect squares, right? Because now you've got x times x. Now you've got 5 times 5. So that part of the parentheses would be x plus 5. And then x minus 5. And the 2 that was hanging out in front, well, it's going to do the same thing here. It's still just going to hang out in front to be there. Okay, so worst thing they might have you do is kind of do that where that maybe before you can get to the perfect square part, you've got to take out a greatest common factor. All right, now here's where they take 1 and go kind of one more extra step here. This is going to make you go, a little bit. So you got x to the 4th minus 36. All right, 36 we're good with, right? 6 times 6. But what about x to the 4th? Yeah, x squared times x squared, right? So as long as they give you a number that's got an even power on it, you can just cut it in half, and that makes it a perfect square then for that part of it. So, all right, that's worth it. So for that one, we'll just make it x squared plus 6 and then x squared minus 6. All right, now, and again, because it's perfect squares, it always has to be an even number on your exponent. If that's, now you could possibly have one like this where you might factor out something in the beginning of it, but if you're going to break down and use perfect squares on it, it has to be this power here, your variable has to be an even number. So you can do x to the 2nd, x to the 4th, x to the 6th, x to the 8th, and then you can always cut it in half for that part of it to get there. Okay, so different special cases, I guess you could say. And for these, there's not really anywhere to put this on the paper because our paper's filled up now. So if you want to take out a sheet of paper, we'll just kind of go through and do some special cases of factoring, just so we can kind of see what happens with it. Okay, probably one of the big ones that we've got. It's the just like we did this one a minute ago, that was a difference of perfect squares. When we're doing the two terms with this one, there's a couple of them that's three terms. And it's the sum of perfect squares. But it's a perfect square trinomial. And this is kind of going back to the one we were doing yesterday, if we were going to do one like this. Let's do it this way. Let's do 16b squared plus 40b plus 25. Okay, because the very first thing you're probably going to think is you're going to get one of these numbers and you're going to be, oh, we're going to do the 8, because there is no greatest common factor, so there's nothing we can do with it because we were close. We had 16, 40. You know, if this had been 24, we could have gone back and divided all the numbers by, 8. 4 would have worked, 2 would have worked, but 8 would have been the biggest number we could have pulled out of it. But in this case, there's not. And you start multiplying, you go, all right, well, that's 16 times 25, and you go, all right, that's 400. And you're like, do I really want to start breaking down 400? Probably not, but here's what we want you to kind of notice on this one. If the first and the last numbers are perfect squares, then you've got a shortcut you can probably do. All right, and there's a couple of different ways you can do this one, but if you want to kind of think about it this way, and we'll show you the form that goes with this one, is that if these are perfect square numbers, there's a really good chance that this 16b is going to be basically just 4b times 4b, and the 25 is going to be 5 times 5. Okay, and then if you wanted to kind of check it for this thing, here's basically what you would do. Because we know if we do 4 times 4, that would be 16. If we do 5 times 5 with the full method, we'd have that one. But basically, if you just check these two numbers, multiplying these together, if we do 4 times 5, that's 20b. 4 times 5, that's also another 20b. As long as those two things add up to your middle number, then it works. Okay. Now, if it doesn't work, more than likely it's going to be prime, because there, if it numbers, really, if it starts getting in the where it's like, 800 or 1,000 or 1,500 or some big number like that, I'm not expecting you to take 1,200 and break it down and start finding all the factors on that, because that could take a while. So if you start getting one of these and you get a really big number, then you go, well, maybe there's a shortcut for this thing. And again, you got to kind of notice that the first and the last numbers are still perfect squares. All right, so the final answer for that one would then be, because it's the same thing twice, would just be 4b plus 5 squared. Okay. The other thing they can do with this one, instead of being the sum of perfect squares trinomial, it could be the difference of a perfect squares trinomial. And it's almost exactly the same thing, except for there's one little minor thing that's different about it. That now, again, if it's a perfect square number, the way they set this thing up, it's still going to be that the first number's the same, the second number's the same. The big difference is for this one is that, let's do it this way. Let's do 100x squared minus 180x plus 81. Because this would definitely be one of those where you got to know the shortcuts. Because if you did the AC method, you would do 81 times 100. I'm not expecting you to take 8,100 and break it down and start finding all the factors on it. I'm not that crazy. Might be a little crazy, but ain't that crazy. Okay, so for that one, that's when the light bulbs in your head should start going off. Okay, there's probably something here I can do that's shorter. And again, if you think about it, you've got 10 times 10, you've got 9 times 9. And basically, here's the shortcut. If they say that this thing is a perfect square trinomial, if you go back to what we were doing when we were factoring this thing the other day, basically their check is that if you do 2 times the square root of A times the square root of C, if that equals the B term, then you got a shortcut. And some people go, well, I'd rather just go back up here and just do this times this and this times this and see if those two things add together to be my middle term. And that's fine. It's doing the same thing. It's just doing it a different way. So according to their thing is that if you do 2 times, well, the square root of the A in this case would be 100. The square root of C is 81. And the question is, all right, if I do that, does that come out to be the B term, which is 180? Now, if the middle term is negative, sometimes they'll do like an absolute value, the B term, because it depends on if that B term is positive or negative. Kind of depends on what we're doing here. So if we do 2 times 10 times 9, does that equal 180? Yeah, it does, right? So then if it does, then we get to do the shortcut. So then it's just 10 times 10. And then 9 times 9. All right, now the catch with this one is that if you notice the first and the last numbers are both positives, but the negative's in the middle. So if it's a perfect square trinomial, whatever the sign is in the middle, whether that sign is negative or positive, that sign will always go in the middle of your expression back here. It would be that. Okay. And again, sometimes you'll really notice, like this would be one that if you start to do the AC method, you would look at it and go, no, I'm not going to do that. But a lot of times if it's a smaller one, sometimes people don't notice it as much just because the numbers are small, and that's fine. Sometimes you'll do one and you get to the end of it and you'll go, oh, well, that was just the same thing twice. And you're like, well, that was weird. And it's not really noticeable. But sometimes, again, if the numbers are really big when you do your AC method, it should just kind of jump out at you as like, okay, here's, definitely this one was something that we could have done something else with it. So, okay. So that's kind of the two, some problems that, again, sometimes, it's going to save you some work, especially when your A and C numbers are kind of big. That, again, I'm not expecting to take 8100 and break it down and start finding the factors on. That's just kind of ridiculous. Okay. And then I think pretty much everything else as far as just the regular factoring is just giving you some different options and having you just play around with some different numbers. It may be that you've got a problem that is something like this. Minus 4x squared plus x. Because we didn't really look at one quite like this yesterday. But first thing with this one is, again, if you go back to our trinomials yesterday, that what we said we were going to do is you always put the terms in descending order. You're always going to look for a greatest common factor first. Doesn't really matter what it is. So in this one, terms are in descending order, but they all have an x in it. So very first thing you would do is go back and divide everything by x, which means you'd have to take an x out of every single one of them. And just remember at the end, when you divide this part of it by x, that you've got x divided by x, it would cancel out, but you've still got to put that one in there like as a placeholder, because if you've got 3 terms here, you still need 3 terms here, because sometimes people will leave that one off. And I'm like, well, that's fine, but you had 3 terms here. If you do distributed property back in, now you've only got 2 terms. So if this thing cancels all the way out, you still got to put a 1 in there as a placeholder. Okay, and then from there, that comes back to basically like we were doing yesterday. Now on the inside of it, it's just a trinomial, and you can factor this one, ever how you want to. If you look at this one, it's more kind of like we were doing yesterday. This is a bottoms up or AC method that you could do. You may also look at this one and go, well, isn't that a perfect trinomial? Because this is 2 times 2, and that's 1 times 1. So maybe one of those where you can kind of look at it that way and go, oh, yeah, that definitely could be. Because you've got 2x squared. Well, that's 2x times 2x. 1 is the smallest perfect square number because it's still 1 times 1. And if we kind of go with that 2 times the square root of a times the square root of c back here, there's your square root of the a term. There's your square root of the c term. And does that equal 4? Well, it does, right? Put the 4x on there. So that one, even though the numbers are really small, it still is a perfect square. A perfect square trinomial when it comes off of it. So that one could be x times 2x minus 1 times 2x minus 1. So again, that would be 2x minus 1 squared. And a lot of times when the numbers are really small, you don't notice it as much. And again, if you did the AC method on this, it would be fine. It probably would take about the same amount of time. Because you would do 4 times 1, figure out that's 4, and then the factors of 4 that equal negative 4, well, that would be 2 and 2. And then you've got your numbers, and you can go back and do the bottoms up on it. But even when the numbers are really small, sometimes, you can still kind of notice if they're still perfect square numbers, then you can still kind of make some shortcuts there. Good. Some people are like, well, do we have to do the shortcut if we, would it be wrong if we didn't see the shortcut on that one? No. Even if you still do factoring with the bottoms up method and go with that route, just, if you don't see that it's a perfect square number, it's not going to count wrong when you're factoring this. As long as you got it factored in some way, shape, form, or another, it's fine when it comes off of it. Now, sometimes we'll get to doing problems like this, and sometimes people get so locked in on doing these that, it's going to ask you to factor. And let's see. That the first thing that people will do is they'll look at this one and they'll go, okay, so we've got 9x to the third minus 6x squared plus 2x. Obviously, everything's got an x in common, so you can factor that out. So we've taken x out of every single one of them. We've got this. And then now we're back to kind of checking it to see, what we've got here. Now it's just a trinomial part that's here. That's a perfect square, but that one's not, so we can't do the perfect square shortcut. So then it becomes, all right, we're going to do the AC method. So we've got our A is equal to 9, our B is negative 6, and our C equals 2. So if we do the AC method, that's 9 times 2 for 18. So it's the factors of a positive 18. We need the sum to equal negative 6. All right, and just going back and checking like we did yesterday. If this 1 and 18, B term is negative, so that sign always goes with a bigger number. If we divide a positive and a negative, that means the other number's got to be a negative. So in that case, they're both going to be negative. So then if we do 2 and 9, both going to have to be negative. If we do 3 and 6, they're both going to have to be negative. Okay, so any of them add up to negative 6. We don't, right? So in that case, that would be one of those that if you take out this factor of x, that's all you can do. And sometimes when you're running through these problems, taking out the greatest common factor, that may be it. There may not be anything else you can do with those. And then you're just kind of stuck with that number, and that's it. So, so just because it asks you to factor when we're going through some stuff, most of the time it's going to have you do one more step after that you should get some stuff that will factor. But occasionally, sometimes you take out a greatest common factor, and that's it. That's all there is that you can do with that problem. All right, so we're going to do the sum and the difference of cube numbers. And again, this is that special attachment, that special tool that you're only going to use every so often when it comes off of it. Okay. So here's what it's going to look like. And the beginning of it's going to look really, really simple. It's going to be the sum or the difference of two cube numbers. So it's going to be a to the third plus b to the third, or in a minute we're going to do one where it's a to the third minus b to the third. And it's one of those things that if you do it this way, there's only one answer that gets from this one, and it's the same answer that kind of goes through this one. That what you're going to do is, if it's a to the third and b to the third, whatever this number is to the third power is just that number or that variable. Same thing with b to the third. It's whatever the b number is without the cube on it. We're going to add those two things together. And then in the second parentheses, it's going to be a not to the third power, but a squared. The last number at the end is not going to be b to the third. It's going to be b squared. And in the middle, it's going to be minus ab. So it's going to be a plus b. So a cubed plus b cubed. Whatever the sign is here, it's going to be the same thing here. We're just going to take off the cubes. And it's going to be a squared minus ab and then plus b squared. Okay, and if they ask you to factor this thing completely, that is all that you do. There's nothing else you can do to it. And it seems like you can do more to it, but you're not able to. So that's your formula if you want to kind of think about it that way. If you look in any math book, anywhere, that's what they call the formula for it. So let's give you like an example of it where you've got some numbers. Let's say you're doing x to the third plus 27. Because this will be more like what you'll see when we go through our stuff. All right, so very first thing is, if you've got 27, everybody okay if that's 3 to the third? Okay, so basically everywhere we've got an A, we're going to have an X. Everywhere you've got a B, you're going to put a 3. So that means this thing is going to be X plus 3. Again, instead of A squared, it's going to be X squared minus X and 3, and then plus 3 squared. Okay, and the only thing you can do to that thing is just clean it up just a tiny little bit. Where you've got x times 3, well, let's write it like we're used to seeing. Let's write it as 3x. And where you've got 3 squared, you make it 9. And that's it. That's all you can do to it. And that's one of those things where it's a special tool that you will only use it once or twice a year, and that's it. I've asked some of the people that I remember in pre-cal when we do this. Sometimes when I was teaching pre-cal, this would be one of those problems where sometimes you would do some other factoring and you'd get to something, and then you'd have to use this literally like twice in a whole year of doing pre-cal. So it's just a weird little special tool that you'll use every now and again, but you just won't use a lot. But occasionally you will use this thing. Okay. Now, if it's the difference of two cubes, it's almost exactly the same formula, but you just have to change a sign or two. All right, so for the formula for the difference, it's going to be a cubed minus b cubed. Okay, and really the only difference is you're going to swap where this was a plus and this was a minus. You're just going to switch these two signs. Now, the first one's going to be a minus and the second one's going to be a plus. So whatever they give to you here with a cubed minus b cubed, you take the cube powers off, and then it's going to be just a minus b. Just like back here, we took off the cube powers and made it a plus b. So this sign always matches up with the first parentheses. And then it's a squared and then plus ab. And this minus here will take care of it when we multiply it back here. So then it would be just that with a plus b squared at the end. So exact same numbers, exact same everything except for the only thing you're going to do different from a sum to a difference is you flip flop the first two signs. Everything else is exactly the same. All right. So if it was y to the third minus 125. All right. Y to the third, we're good. 125 would be 5 to the third. So now everywhere we've got an A, that's really going to be a Y. Everywhere you've got a B, that's going to be a 5. So that's Y minus 5 times Y squared plus. Now we're going to do Y times 5 or 5 times Y if we stick to the numbers on that one. But wait, did I do it the wrong way? No, it should be, yeah, Y times 5 if you put it in order. But if you do Y times 5, let's go ahead and rearrange it and make it 5Y because that's the way we're most of the time used to seeing it. And then if you do 5 squared, oh, let's go ahead and make that 25. Okay, and that is it, because again, a lot of times we get there and we start trying to break this thing down. But if you start to break this down, there are no factors of 25 that's going to equal 5. And so you just have to kind of leave it there. Okay. And pretty much the only thing that they would wind up doing is maybe tweaking a few numbers here and there. Probably worst case scenario, they may do something like this, where that instead of it being just x to the third in the front, it may wind up being like 8x to the third. If you do that, that would be 2x to the third power. And then 27 would wind up being 3 to the third power. Okay. Now, if you have that one, that is going to make that a little bit more difficult because of just the extra number here in the front, kind of throwing that one off. Okay, so first parentheses would still be the same. It's still going to be this thing minus this thing without the third powers. But then the next thing is going to be the 2x squared plus the first thing times the second thing, and then plus the last thing squared. Okay, now if they give you that one, there's a lot more stuff to do inside here other than just doing, a few little things like we're doing before. 2x minus 3, we're good. If you do 2x squared, that would be 4x squared. 2x times 3 would be 6x, and then 3 squared would be 9. All right, and again, it seems like you could do more with this one, but on the perfect trinomials, or the sum of cube numbers or the difference of cube numbers, there's nothing you can do to break that down. That's it. That's all you can do with it. And again, you don't use that a lot. There may be one time the rest of the year that we'll do some factoring and that will pop up, but it just doesn't happen a lot. It's just one of those things of just kind of knowing that it's there, that if you ever need it, it does pop up there.